Okay, calculus class. So today we are going to start 7.3, looking how differential equations can model growth and decay functions. So for this, it's going to talk a little bit about proportionality. For instance, the rate of the change of some quantity y is directly proportional to that y. Or as you can see, let's just write this, I guess, 7.3. Differential equations growth and decay functions. Okay, so the first thing that we'll want to talk about is the law of exponential change. So if y is a differentiable function of some time, or t, such that y is greater than 0, so you have to start with a quantity. For both growth and decay, you have to start with something greater than 0. And for some constant k, then you can get the equation y is equal to c, which is just a constant, and then e to the kt. C is the initial value of y. And again, this needs to be greater than 0. And k is the constant of proportionality. Constant of proportionality. T is obviously time. So when k is greater than 0, that is when you're getting exponential growth. And when k is less than 0, that's when you're getting exponential decay. And I know that y'all have worked with exponential growth and exponential decay functions in math as well as in science. But now we're going to look at how does this relate to differential equations. So if we think about our differential equation, so let's first think about, okay, we have some change in y is dependent on some change in t at some proportionality constant, k, for some value of y. So let's prove that some rate of change of this quantity y with respect to t is actually proportional to y itself. So prove essentially that this supports what we just wrote of y is equal to c e to the kt, or our exponential growth / decay function. So if we have dy dt equals k times y, then similar to last section where we were separating variables, we need to move y to one side and we need to move t to the other side. So if we move y to the left, we get 1 over y dy is equal to k times dt. Now k is just some constant of proportionality, so it doesn't matter. It's not like another variable, so it doesn't need to be dk. It's okay that it is dt with respect to time. It's just a constant. So now we can go ahead and integrate both sides. We get the integral of 1 over y is natural log of y plus some constant is equal to a constant k times time, our variable of integration, plus our second constant. So we get that the natural log of y is equal to kt plus c3. So now we need to do e to both sides so that we can get that y is equal to e to the kt plus, I guess, plus c3. Now this is the same thing as saying y is equal to e to the kt times e to the c3, according to our rules of exponents. And if we want, we can now bring this, say that this is just e, which is a number, to some constant, which is just another number. So this is now going to be our initial value, or what we're going to call c. So we get that y is equal to c times e to the kt. So some things just to remind ourselves of what we've learned here, because we're going to be using this a lot in exponential growth and decay functions, is that, so let's just write this down as some notes. You can write these off to the side if you want. The integral of 1 over u du is always equal to the natural log of the absolute value of u plus c. And then another thing that we used in this problem was our definition of exponent, or e to the x is equal to y, is the same thing if you rewrite that from exponential form to logarithmic form. That is equal to the natural log of y equals x. That's just our converting between the two forms. And then another thing that we used in this problem was our property of exponents. So if you have some base b that's to the m plus n, that is the same thing as base b to the m plus base b to the n. And then the last thing that we did was say that e to the c was our constant, quote unquote, c. So those are the three properties that we used in this proof of dy dt equals k times y, and going to the exponential form, y is equal to some constant c, e to the proportionality constant times time. So let's move on to a couple examples about how this works. So if we know that the rate of change of y is proportional to y, so let's write that. If we know that the rate of change of y, so it's dy dt, is proportional to y, so k, which is the proportionality constant, times y, and then we just proved that that's the same thing as saying y is equal to c e to the kt, then when t equals 0, y equals 3, and when t equals 2, y equals 6, then when t equals 3, what does y equal? So let's just think about this. The first thing that we know is if we look at this equation, we know that our big value for c is our initial y value. So when time is equal to 0, we know that this is what y is equal to, right? So that means that 3 is equal to c e to the k times 0. Well, that goes to 1, or we've just proved that 3 is equal to c. So now, the only thing that we're missing in our function is what is our proportionality constant. So I guess step 1, find c using initial conditions. And that's what we just did. Step 2, we need to find our other variable that we don't know, which is k. Find k, our proportionality constant. So we need to plug in two different values to figure out what k is. So let's do, when t is equal to 2, we know y is equal to 6. So if we say, okay, 6 is equal to, we know that c is 3. Then we have e to the k times, and then this is when time is equal to 2. Okay, so we can divide both sides by 3. We get 2 is equal to e to the k to the 2k, I guess. And then if we rewrite this using our change between our exponential form and our logarithmic form, you can solve for k, right? And we get that the natural log of 2 is equal to 2k, or that k is equal to 1/2 natural log of 2. Great. So now we can say, what is our actual model for this exponential growth? Step 3. Guess it will be either growth or decay, depending on what your constant is. So it doesn't matter if it's a growth or decay problem, you can use the same thing. So we know that y is equal to, and we know what c is, it's 3. And then we know what k is, it's 1/2 natural log of 2 times t, which I guess we can rewrite that to say 3e to the natural log of 2 to the 1/2, or just the square root of 2 times t. So there's a nice model for us. Now using this model, we can now answer our original equation of what is y when t is equal to 3. So now if we just plug in, we're asking, okay, well, what is y when t is equal to 3? So we get 3 times e, natural log of the square root of 2 times 3, because that's the time that we care about. This is something that you could plug into your calculator, and you would see that at time is equal to 3, you get approximately 8.49. So let's just check to see that this is in fact exponential growth. If we have a graph and we have time versus amount, at 0 we started at 3, and then at 2 we went to maybe 6, and then at 3 we're going to 8. So this would look like this, which is a pretty nice exponential growth graph there. Okay, good job, team. Let's go to another example. This is an example I love to use in class, is talking about bacteria growth. So if the number of bacteria is growing at 3,000 e to the 2t over 5 per unit of time, and at t equals 0, the number of bacteria equals 7,500. Find the number of bacteria at time equals 5. This should be fun. So the first thing that we're going to do is say, okay, we know that the rate of change, because this is the bacteria that's growing at this rate. So we know that the rate of change is the number of bacteria with respect to time is going to be equal to, and then the rate of change equation that you're given, 3,000 e to the 2t divided by 5. Okay, so now this is where a differential equation comes in. We need to, in order to figure out the number of bacteria, we have to separate variables and integrate. So we get dB is equal to 3,000 e to the 2t divided by 5 dt. And now that our variables are on the right sides, we can integrate both sides, and we get b, or the number of bacteria, is equal to 3,000 e to the 2t divided by 5, and then chain rule this. You're going to have to do times 5 halves. or we get that b is equal to 15,000 divided by 2, so 7,500 e to the 2t over 5. Now this should make sense to us because what we know is that our general equation for exponential growth or decay is that y is equal to c e to the kt. And what I gave in our problem was that the initial number was 7,500, right? And that's what we found by integrating, so that's good. So what that means is that our proportionality constant must be 2/5. Because that is our 2/5 times t. So that's kind of nice to double check this. So now, if we want to know, okay, what is bacteria, the number of bacteria at time equals 5, we're going to go ahead and plug this in. We get 7,500 e to the 2 times 5 over 5. So bacteria at time 5 is equal to 7,500 e, the 5's will cancel out, so just essentially e squared. If you plug this into your calculator, the bacteria number at time 5 units is equal, or approximately equal, I'm going to round this to nearest bacteria cell, is 55,418 bacteria. Okay, there we go. Let's just do a couple more examples here. If we have, let's do an economic example now. So if we have a slow economy and it caused the company's annual revenue to drop from 530,000 in 2008 to 386,000 in 2012, and we assume that this pattern is going to follow an exponential decay pattern, what is the expected revenue for 2013? So this would be a great doomsday problem for your boss. It's a joke. Please don't ever model a company's revenue as exponential decay. That would not be good. Okay, so revenue 2008. Oops. It's going to be equal to 530,000. Revenue 2010 is unfortunately 386,000. And revenue 2013 is equal to something that we don't know. So assume exponential decay. Okay, so if we're assuming exponential decay and we know these things, what I'm going to say is that time 0 is 2008, which means that my initial value, C, is equal to 530,000. So now if we plug this into our model, we would say, okay, y is equal to 530,000 e to the kt. So that was step 1, finding what C is. Step 2 says, okay, well, now we need to find our proportionality constant. So our proportionality constant, let's use the next set of data points that we have, which is 2008, 2010, and 2010 is 2 years past what we've designated as time 0. So we know that at time 2, that our y is equal to 386,000. So if we plug this in to figure out our proportionality constant, we get 386,000 thousand is equal to 530,000 e to the 2k, because this is 2 years later. Wonderful. So now we can divide by 530,000 and reduce, and you get 386 over 530 is equal to e to the 2k. If we take the natural log of both sides, get the natural log of 386 over 530, beautiful, is equal to 2k. So we get 1/2 natural log 386 over 530 is equal to k. What a beautiful proportionality constant. If you plug this into your calculator, you can do it now, or if you want to wait so you don't have to round your answer, you can do it later. This is approximately equal to a negative 0.15852. This is a good double check that it's negative, because for exponential decay, k should be less than 0. So if you're doing an exponential growth problem and it turns out to be negative, you should double check your work. If you're doing an exponential decay problem and k does not turn out to be negative, you should also double check your work there. Okay, so the last step is now we're trying to figure out, okay, what is revenue at time, what is that, 5? Because 2013 is 5 years after 2010. So it's going to be equal to 530,000 e to the negative 0.15852 times that time. So if we plug this in, we get $913.16 expected revenue. There we go. And let's do last example of this one. Suppose a population of insects increases according to the law of exponential growth, which is a fair assumption until resources run out. There were 130 insects after the 3rd day of the experiment and 380 insects after the 7th day. Approximate how many insects were there in the initial population. So, if we have insect number on day 3 equals 130, and insect number on day 7 equals 380. So this I'm going to translate into essentially a 0.3130, and this one into a 0.7380. Oops. And we're assuming exponential growth, right? So we can say we know our y is equal to ce to the kt. So if we look at this, what we have is unknowns is c and k. But we do have 2 different equations, right? We have 0.1 and 0.2. So let us try to solve for these. So let's plug in, I guess, our first equation there. So if we use our first set of points, then we will say, okay, 130 is equal to c e to the 3k. And let's go ahead and solve this, I guess, for c first. It doesn't matter which constant we solve for first. So if we divide this by e to the 3k, we get that c is equal to 130 over e to the 3k. Beautiful. I'm going to just rewrite that because I don't like the way it looks. Okay, so now let's plug this in to our equation and plug in our other point. So if we know that y is equal to 130 e to the 3k times e to the kt, and we're going to plug in our second point, so we know that this is 380 is equal to 130 over e to the 3k times e to the 7k. Let's go ahead and say, okay, then that's equal to 380, oh, whoops, don't need to copy that down. This is equal to 130 e to the 7k over e to the 3k. Well, this will become e to the 4k according to rules of exponents. So I have that this is equal to 130 e to the 4k. So if I have 380 is equal to 130 e to the 4k, I now only have one unknown, so I'm going to take the, oops, not yet. I'm going to divide both sides by 130, and I get a 38 over 13 is equal to e to the 4k. And I take the natural log of both sides, and I get the natural log of 38 over 13 is equal to a 4k, or k is equal to 1/4 natural log 38 over 13, and if you plug that into your calculator, you'll get 0.26815. You can also leave it and plug it in at the end if you want as well. So this is a good double check that this is a positive k value and we are having exponential growth. So now let's figure out what our initial amount was. So we're looking for what is y at some time. Well, first I guess we need our c, so we'll plug this back in. So if we know that y is equal to c e to the kt, and we now know what k is equal to, then we can solve for what c is equal to. Oh, goodness gracious. So we have I guess already solved for c up here, so let's use that equation first. Now if we take this c, right, we get that we have c is equal to 130 e to the 3, and then times the k value that we just found, which is, oops, 0.26815. So if you plug that into your calculator, let me plug that into my calculator. Okay, 130 divided by e to the 3 times 0.268159. I get 58.15, but this is in number of insects, so if I round it, 58.15, which is going to be 58 initial insects. Okay, this is a good stopping point for the first half of this lecture, but I'm going to go ahead and finish these notes. You're welcome to continue on if you would like as well. What we're going to talk about next is half-life, which I know that you've seen hopefully in biology and possibly chemistry. But if we talk about half-life, Half-life is a special type of exponential decay function. And what we say for half-life is if A of t is equal to A naught e to the kt with k less than 0, because with half-life your isotope is decaying, then the half-life of A, whatever atomic element it is half-life equals the natural log of 2 over k. So I'm sure that y'all have done several of these types of problems before in science, but let's do a couple examples here. Our first example will say a zircon sample contains 4,000 atoms of the radioactive element 235U, or uranium-235. So we have U-235, which is a radioactive isotope of uranium, and there are 4,000 initial atoms. If we know that U-235 has a half-life of approximately 700 million years, how long would it take to decay to 125 atoms? Okay, well, if we know that our number of atoms is equal to the initial number of atoms, or A sub naught, and we know that we have, or I guess we should, sub naught e to the kt, so this is our model that we'll be using. Let's talk about things that we know. We know that the half-life is equal to the natural log of 2 over k, and we know that our half-life, so our formula for half-life, is equal to the natural log of 2 over k. And in this case, we know that our half-life is 700 million years, so we'll remember that we are in millions of years here. And then we know that at time equals 0, that the number of atoms, so A sub naught, is equal to 4,000. And what we're trying to find is, okay, well, how long does it take for A to be 125 atoms? Okay, so do we have all the information that we need? Let's go ahead and solve this for k. K is equal to natural log of 2 over 700 million years. Okay, so we know that A is 125 atoms is equal to our initial number of atoms of 4,000, e to the natural log of 2 over 700 times t. So we will get, actually, it would be probably easier to solve this for E, but that's okay. Let's go ahead and bring this over, and we get 125 divided by 4,000 equals e natural log of 2 over 700 times t. We'll take the natural log of both sides. We have the natural log of 125 over 4,000 equals natural log of 2 over 700 times t. And now if we solve for t, we get 700 over the natural log of 2 times natural log of 125 over 4,000 equals t. I'm going to need to plug this into my calculator. Okay, so 700 divided by natural log of 2 times natural log, 700 divided by natural log of 2 times the natural log of 125 divided by 4,000. Uh-oh. I got a negative answer, which means I dropped a negative somewhere. Where did I drop it? Should be a negative natural log of 2. Yes. So if we have the half-life equals 700, which is natural log of 2, I should have put that as natural log of 1/2. Bummer. Okay, yes. So assuming I wouldn't have dropped that negative, we end up with a time is equal to 3,500 million years to decay from 4,000 atoms to 125 atoms. Okay, let's do one last nice heat transfer example. So, for this example, a cup of hot chocolate is placed on a table and it cools at a rate. So cooling rate, get it? Cooling rate is dC dt. So the change in Celsius, or I guess this is Fahrenheit, so the cooling rate is equal to a negative 0.05 and then C minus 75 per minute. So this is in degrees of Fahrenheit per minute is our cooling rate. C is temperature and T is minutes. So if the coffee is 160 degrees, whoa, there we go. If the coffee is 160 degrees Fahrenheit initially, so at time 0, what is the temperature 10 minutes later? So we're going to integrate this just to prove to ourselves that it works. So let us bring this equation separating the variables, and we get dC is equal to negative 0.05 C minus 75 dt. Well, that is not I have a c on the variable where it's a dt, so I need to divide by that. And I get 1 over c minus 75 dc is equal to a negative 0.05 dt. And now my variables are separated correctly, so I can go ahead and integrate this. This is 1 over u on the left side, where u is just a c minus 75, so that will become the natural log of c minus 75 plus a constant, but we'll put a constant on the other side already, negative 0.05 t plus that constant, c1. So now let's solve for c. So we get, if we take e to both sides, we get c minus 75 is equal to e to all of this. And remember that the note that we did at the beginning of the first example of this problem, we can go ahead and say that e to the c1 is going to be our c. So I'm going to say, okay, c e to the negative 0.05 t. And so I can say then, if I add 75 to both sides, that my equation for the temperature, C, is equal to the original temperature, e to the negative 0.05 t plus 75. Okay, let's go ahead and bring this up here. If I know that my temperature at time 0 is equal to 160, then I can say that CE to the negative 0.05 times 0 plus 75. This goes to 1. I'll subtract 75 from both sides. And I get that 85 is equal to my initial temperature. So then my equation becomes C of T is equal to 85 e to the negative 0.05 t plus 75. And I can now solve for 10 minutes later. 10 plus 75. So if I plug this into my calculator, I get that my temperature is approximately 126.555, or I'm just going to round this to the nearest degree. That is approximately equal to 127 degrees Fahrenheit. So if it started out at 160 degrees, 10 minutes later it will have decayed to 127 degrees. This is it for our exponential growth and decay functions. So you can go ahead and get started on homework 7.3. And we'll only have one more section before we're done with calculus and start reviewing for the AP exam.